Hello everyone, this is my presentation for the IBM Advanced Data Science Specialization. My name is Andrés Rosero and I will talk about the implementation of a credit scoring model. I will first talk about the problem definition, then I will show the available data and some details about it. After that I will talk about the methodology that I used to solve this specific problem. Then I will show the process model implementation with all the notebooks that I created for this purpose. And at the end, I will show the deployment of the solution, which is currently serving on-demand predictions. So the idea was to build a model to predict if a credit applicant was a good or a bad customer, or if you prefer, to identify good payers and defaulters. However, there was no clear definition of good and bad in the original datasets, so I had to create one label by myself by looking at the details in the available data. There were two datasets, one containing information about applications and applicants, with information such as the number of children, the amount of income, the occupation type, etc. And another dataset containing information about historic payments of each of the customers of this hypothetical bank. So I decided to use this dataset to create the label by defining that anyone with an overdue of over 60 days was considered as a defaulter or a bad customer. Then I joined both datasets through the client ID field, and I ended up having one single dataset with all the features and labels. You can see more details of each of the original datasets in this slide. Regarding the methodology, I used the lightweight IBM Cloud Garage method for data science, which in brief consists of two main components, which are the architectural decisions and the process model. In the architectural decisions, one should decide, for example, the data integration technologies and tools and the data sources, etc. And in the process model, one should follow these steps that you can see on the right side to achieve consistency and to end up having a good quality data product. Regarding the data source, I extracted the datasets from Kaggle. I used the Kaggle API to achieve this systematically. The datasets were originally in CSV format, and I decided to convert them into Parquet format for easier use and faster loading times. About the data integration part, I decided to use my own computer, so it was everything was built with local processing to train the models and to create them in general. I also used the pipeline abstractions provided by the scikit-learn API because I think that it is important to use this kind of abstractions to increase observability and modularity of all the code that we create. Regarding the apps and data products component, I created several model MVPs by using different libraries such as XGBoost, LikeGVM, and scikit-learn. I also created and deployed an API in Google App Engine for on-demand predictions. This could be achieved by using any ML managed service, but I decided to create an API by myself. So now I will show the process model implementation with all the notebooks. It is a lot of code, so I will show it really fast. In here you can see that I created one single notebook for each of the steps in the process model workflow. So in the first notebook, I fetched the data by using the Kaggle API. Then I create the label by using the definition that I mentioned earlier. Then I remove some duplicates. After that, I merged both datasets by using the client ID and label fields. Then I once again drop the duplicates in the merged dataset, and at the end I split the dataset into a train and a test datasets. In the train dataset, which is kind of the same distribution in the test dataset, there were around 1.3% of bad customers against around 98.7% of good customers. After that, I saved the datasets and I used the training dataset to perform an EDA. So I wanted to identify what type of features I had, if they were categorical, numerical, if they were high cardinality, low cardinality, etc. I also plotted the distributions for each of the features, their unique values, their correlations, their missing values. So for example, in here you can see that the occupation type has the most missing values with around 30% of the total. Then I plotted the distributions group by label, so you can say that 1 is a bad customer and 0 is a good customer. And I plotted some relations for each pair of features. For the feature creation step, I used the abstractions provided by the scikit-learn API, specifically using the pipeline object. So for the categorical features, I transformed them by using a weight of evidence encoder, and for the numeric features, I only applied a robust scalar scaling technique, because the tree-based algorithms that I was going to use in future steps didn't need to impute missing values, for example. Then in the model definition step, I tested different models or algorithms. So in here you can see a Keras implementation with a very simple neural network. Then I tested an XGBoost classifier, an LGBM classifier, a support vector machine, a random forest classifier, and an AdaBoost classifier. And I ended up having the results for each of these models, running them with their default parameters. The tree-based algorithms were the best performing, so I had that for the following step, which is the model training and the hyperparameter tuning. I used XGBoost, LGBM, and random forest classifier because they were performing very good in the model definition step. For the following notebooks, I won't show them. You can see them in the GitHub repository, and I will go back to the presentation because it is easier to present the results in there. In here you can see the results of the model definition step. I forgot to mention that I used the average precision score as my core metric. I used it because it allows me to compare between different models, and it is also a good fit for cases when you have huge imbalances between classes, like in this one. The tree-based algorithms were the best performing, and from them you can see that the random forest classifier scored the highest in the scale. After identifying that I was going to use the tree-based algorithms, I ran a randomized cross-validation cycle to find the optimal hyperparameters for each of them. However, I found that there was no significant improvement with respect to the default hyperparameters, and in fact there was an increase in training times, so I decided to just use the random forest classifier with its default hyperparameters as my best estimator. Having this best estimator, I used the test dataset and a cutoff of 0.5, and I achieved from there a precision of 0.9 and a recall of 0.85. Those are very good results if you have in mind that this was a very quick development. In here you can see the confusion matrix with normalized values, and you can see that the model is performing very well in terms of false positives, true positives, false negatives, etc. On the right side you can see the distribution of the scores that the model throws. It is very good at classifying the good and the bad customers because the scores are mostly located on the extremes of the score range. Regarding the feature importance, you can see that the model is using all the features, so it is very robust in this sense because it won't be affected by the change of one single feature distribution. You can see also, if we take as an example the days employed feature, that having low values for this feature means scoring higher in the scale of bad customers. So that makes sense if you think about it in the real world. If you have been employed for fewer days, it means that you could be more prone to default in your credit obligations. Regarding the deployment, on the left side you can see the structure of how it is that you get a prediction from the MPI that I deployed. So you send the raw features, you then through the MPI send the structured raw features to the preprocessor and the classifier, which are loaded as a serialized file from cloud storage, and they send back a prediction to the MPI, and the MPI answers with a structured prediction to the client that is requesting the predictions. On the right side you can see an example of that I just explained. So you send the instances with the raw features for each of the observations, and you get back the score for each of those observations. The response time for this call is around 200 milliseconds, which make it viable for productive environments. In conclusion, the deployed model answers the business problem and works as a functional MVP, which was kind of the main objective of this project. However, there's still work to do to improve some details, such as the filtering of possible application duplicates. I found during the EDA stage that many observations had the same feature values but had a different client ID, but it wasn't possible for me to know which were duplicates and which were just coincidence to have the exact same values. And finally, I invite everyone to use the IBM Lightweight Cloud Garage method for data science, because it improves reusability, maintainability, and consistency, and allow us as data scientists to achieve very good quality data products. I would like to thank Coursera, IBM, and Kaggle for providing all the tools and knowledge for me to be able to complete this project. And that's it for today. See you.